Welcome. I am Basis Spelever, and I will present the paper called A Blueprint for Integrating Task-Oriented Conversational Agents in Education. We will start with some background. Over the years, the presence of chatbots and their use in education has increased. However, the technologies and architectures used to build chatbots for education are often not designed for this context. We noticed that there is currently no standard approach to build chatbots for education. So if you were to create a chatbot for education, you could either build it from scratch, which would require advanced technological knowledge, or use an existing framework, though they often lack the pedagogical scaffolding to be integrated in learning contexts. This is why we propose an architecture to address those challenges. Our proposal is most aligned with work by Criol and Callejas, with their Geranium pedagogical system. They propose a speech-based system that integrates into question-based learning applications. Our architecture uses text-based inputs and is agnostic to the pedagogical context and type of interaction. Our proposed architecture is composed of what we call building blocks, that are basic bricks we use to create a complex system. The first element we need is the learning resource. This is the pedagogical context in which the chatbot is embedded. The chatbot is equipped with a function, which is an action that can be performed on the learning resource. We define concepts which are subjects that our chatbot can converse on. To follow the evolution of a learner, we define learning graphs, which are a set of states to represent the learner. There will be one learning graph per concept. We define a channel as the location in a graphical user interface where an interaction between the chatbot and the learner takes place. Our last building block is feedback, which represents an implicit or explicit signal with respect to the quality of the interaction. Our first process is summon chatbot. A learner can request a chatbot to activate by using an element in the graphical user interface that is exposed by the interface engine. The request provides the learning resource, which is passed to the task engine, where the function is run. The output of the function is converted to a list of concepts that the chatbot can talk about. This list is passed to the knowledge engine, which initializes the learner model with learning graphs created from the concept list of the task engine. The learning graphs are passed on to the interaction engine, which selects the appropriate interaction models. These models are stored in the knowledge engine and are processed by the interaction engine to generate a dialogue. The generated dialogue is finally forwarded to the interface engine, which opens a channel in the graphical user interface. This is the process of summoning the chatbot. Our second process is hold interaction. Once channels have been opened, the learner can use one of the channels to converse with the chatbot. Using graphical elements provided by the interface engine, he can send a response to the chatbot. This response is processed by the interaction engine. From this processing, the interaction engine passes updated interaction and learner models to the knowledge engine, which is responsible for tracking the learner's state. Based on the updates, a new dialogue can be generated and forwarded to the interface engine to be posted as a new comment. This is how the chatbot holds an interaction with the learner. The last process is give feedback. A learner can provide feedback through explicit or implicit means. This feedback is sent to the interface engine, which forwards it to the learning engine that is able to incorporate. Feedback will guide the chatbot strategies for choosing dialogues and transitional learner states. And here you can see all the processes together. To validate our architecture, we implemented the code review application. It is an online learning application providing an interface to perform code reviews. Learners had to identify style issues in JavaScript code. Our chatbot was able to provide guidance to students and help them recognize common style issues. A few limitations to highlight. We considered only the case of a single user, single chatbot in a single session. To handle multiple users over multiple sessions, our architecture requires more components. The validation we carried out involved only one learning application, but we plan on targeting more diverse contexts. In conclusion, we contributed an architecture for task-oriented chatbots in education. Our description of the required components and implementation in an online learning application provides a strong base for integrating task-oriented chatbots in education. Thank you very much for listening.